Interstellar comet 3I Atlas is doing things no natural object should be able to do. Its trajectory isn't just unusual, it's precise, adjusting itself to pass exactly through Jupiter's Hill sphere. Its chemistry shows an excess of nickel more typical of engineered alloys than space debris, and its brightness behavior is so irregular that it refuses to match any known model of outgassing. These signals don't line up with randomness. They point to something we've never seen in the solar system before. Stick with me, hit subscribe and drop a like. What comes next will challenge everything we thought we knew about interstellar visitors. When scientists noticed that an object from another star system appeared to adjust its path as it approached Jupiter, they began examining the data with greater care. The visitor, known as 3I Atlas, had already shown signs that it did not behave like a typical comet, but a possible course shift made the situation more unusual. Researchers who specialize in orbits, comet activity, and interstellar chemistry looked at the measurements collected over several months. They searched for simple explanations first, such as small changes caused by sunlight, uneven heating, or measurement uncertainty. When these possibilities did not match the data, the remaining observations demanded closer attention. 3I Atlas had entered the solar system with a path that seemed straightforward at first. As it moved closer, telescopes around the world tracked its speed and direction. Over time, small deviations appeared. At first, most of these were treated as normal irregularities, because many comets release gas in unpredictable ways when they warm near the sunday. But as the object continued inward, the irregularities grew into a pattern. Teams checked the readings from different observatories to ensure consistency. They compared the brightness levels, the shape of the coma, and the direction of the tail. Even with independent methods, the same anomalies appeared. This gave researchers confidence that the data reflected the object itself, rather than errors in their instruments. One of the strongest puzzles involved the projected encounter with Jupiter. NASA's calculations showed that 3I Atlas would reach its closest approach to Jupiter on the 16th of March in the year 2026. The estimated distance at that moment was 53.445 million kilometers. Jupiter's Hill radius, which marks the region where Jupiter's gravitational pull becomes stronger than the Sun's pull, is 53.52 million kilometers. These values are so close that they differ by only a small fraction, within 1 part in 26,000. Because the Hill radius is not a physical barrier but a mathematical boundary, it is rare for a natural object traveling for long periods to approach it with such precision. The Hill radius matters because objects within this region can be influenced more strongly by Jupiter than by the Sunday. Inside this area, a body may become temporarily captured or may settle into a stable orbit. Outside it, the Sun's gravity dominates and tends to pull objects back into solar-centered paths. To reach a zone this narrow, a comet would typically need to approach with a certain speed and angle that aligns well with Jupiter's motion. A small variation in either factor could shift the object millions of kilometers away from the boundary. When the team saw that 3I Atlas was on track to meet this radius almost exactly, they ran simulations to test whether natural processes could produce such a match. The simulations showed that while not impossible, the probability was extremely low. Another anomaly appeared near perihelion, the point where 3I Atlas came closest to the Sunday. At this stage, many comets release large amounts of gas and dust as frozen materials warm and turn into vapor. These jets can act like small thrusters, pushing the comet in unpredictable ways. But the acceleration observed in this case did not match the usual pattern. It was stronger than expected, appeared at a specific moment, and pointed in a direction that aligned the object directly with Jupiter's Hill radius. Without this change, 3I Atlas would have passed the region by a wide margin. Researchers modeled different gas release scenarios to test whether natural outgassing could produce both the timing and the magnitude of the shift. Most models failed to match the observed path. The calculated probability for this alignment was around 0.04%, or 4 chances in 100,000. Even though rare events do occur, this one required careful review. Within the Hill radius lie 2 points known as Lagrange 1 and Lagrange 2. These are positions where the gravity from Jupiter and the Sun balance, allowing objects to remain stable with little effort. Space agencies use similar points near Earth to place long-term observatories because spacecraft there need minimal fuel to stay on station. Lagrange 1 and Lagrange 2 near Jupiter would offer similar advantages. An object positioned at either point could hold its place while using very little energy. Because 3I Atlas seemed to be moving toward these areas, scientists examined whether its motion might be shaped by such gravitational features. They did not assume intention, but focused on whether known physical processes could steer a body so precisely toward such narrow locations. A separate anomaly emerged as the object traveled from July through November. Instead of showing a dust tail pushed away from the Sun, as most comets do when solar radiation forces dust outward, 3I Atlas displayed a narrow extension pointing toward the Sunday. This feature is known as a sunward jet, or an anti-tail. Most anti-tails seen in comet images are optical illusions caused by viewing angles. Dust in the comet's orbital plane can reflect sunlight in a way that makes it appear as if the tail points toward the Sun, even though it does not. But in this case, the feature persisted through different angles and distances. The high-rise camera on NASA's Mars Reconnaissance Orbiter captured images that confirmed the structure was real. The extension appeared ahead of the object in its direction of travel. If it were a natural jet, it would require an unusual internal process to direct material forward rather than backward. Researchers tested whether rotation, uneven heating, or trapped gases could cause this pattern. The models provided partial explanations, but did not match the overall behavior observed across several months. Some scientists suggested that if an object ever needed protection from dust impacts traveling at high speed near 60 kilometers per second, a forward-facing plume could reduce those impacts. This idea remained theoretical, but the persistent sunward extension called for more investigation. The feature did not match well with existing categories of comet behavior and remained difficult to explain with familiar mechanisms. NASA's Mars missions played an important role in gathering additional data. When 3I Atlas passed within about 30 million kilometers of Mars, the Mars Reconnaissance Orbiter, the MAVEN Orbiter, and the Perseverance rover were in positions that allowed them to record information about the visitor. Although these missions were designed to study Mars, their instruments can observe other targets when conditions are favorable. On the 2nd of October, the HiRISE camera on Mars Reconnaissance Orbiter captured visible light images from roughly 0.2 astronomical units away. These images showed a soft, bright region surrounding the object. The coma, which is the cloud of gas and dust around a comet's core, measured about 1,500 kilometers across. The core itself remained blurred because of limitations in resolution and brightness, but the structure of the coma gave clues about the flow of material around the object. MAVEN, which observes in ultraviolet wavelengths, monitored 3I Atlas over 10 days from the 27th of September to the 7th of October. Ultraviolet light can reveal signatures of different molecules because many gases reflect, emit, or absorb light strongly in that range. By studying how the ultraviolet brightness changed over time, scientists built a chemical profile of the gases released from the object. These measurements provided details about the proportions of metals, volatile compounds, and other materials within the plume. Even the Perseverance rover contributed. From the surface of Mars, inside Jezero crater, the rover captured faint images of the object on the 4th of October. The exposures had to be long because the object was dim from the ground, and scattered light from the Martian atmosphere reduced its visibility. While the images did not show detailed structure, they confirmed that the object was in the expected position and offered brightness measurements that supported the data from the orbiters. When the chemical composition data were combined, researchers found that the plume contained much more nickel than iron. This ratio was unusual compared with thousands of known comets. The nickel to cyanide ratio was also far higher than values measured in other bodies, including the earlier interstellar visitor 2I Borisov. The pattern resembled certain nickel-rich alloys rather than typical natural mixtures. This observation did not lead to firm conclusions, but it suggested that the material in 3I Atlas formed under conditions that differ from those in most comet families. Another unusual feature was the amount of water present. The plume contained only about 4% water by mass. The amount of water found in the plume marked a clear break from what scientists usually see in comets. Most familiar comets within our solar system carry large amounts of water ice, often forming the bulk of their mass. When they warm near the sun, that ice turns into vapor and drives much of their activity. With this visitor, the measured water made up only about 4% of the total mass of the plume. That level is far below what researchers expect from a body that behaves in many ways like a comet. Because of this, scientists began to look for explanations that could account for such an unusual composition without assuming an unusual origin. One possibility discussed was the buildup of material over long periods. An object traveling between the stars might spend millions or even billions of years moving through cold, dusty regions of interstellar space. During that time, tiny grains, thin layers of ice, and stray molecules could accumulate slowly on its surface. As sunlight warms these outer layers after entering the solar system, they may release gas and dust that do not reflect the true interior composition. In this view, the plume might come from a surface coating rather than from the core. Although this idea does not solve every puzzle, it provides one natural pathway that scientists can test with further observations. The mass of the object introduced another set of questions. 3I Atlas is estimated to be roughly 1 million times more massive than the first known interstellar visitor, Oumuamua, which researchers pronounce as Oumuamua, and about 1,000 times more massive than the second visitor, 2I Borisov. Despite carrying so much more mass, it moves through the solar system at a speed greater than both of them. In astronomy, large objects usually require significant forces to accelerate or decelerate. High mass combined with high speed suggests a long and powerful journey, shaped by conditions far from the Sunday. Researchers also examined whether this mass is consistent with the expected distribution of rocky material drifting between the stars. According to current models, there should not be enough loose solid matter in interstellar space to routinely send such a large object into the inner solar system once every decade or so. The numbers do not align well unless the arrival rate is lower than what we have observed, or unless this object's presence here is not the result of random processes alone. This does not imply intention, but encourages scientists to consider whether there might be unknown mechanisms that direct interstellar bodies towards systems like ours. The path of 3I Atlas through the solar system also stood out. The object moves in a retrograde direction, meaning it travels opposite to the direction in which the planets orbit the Sunday. A retrograde path is uncommon, but not unheard of. What drew greater attention was its orientation relative to the ecliptic plane. The ecliptic plane is the flat, disc-like region defined by the orbits of the major planets. Most natural visitors from interstellar space arrive at steep angles compared with this plane. 3I Atlas, however, approached within about 5 degrees of the ecliptic. Researchers noted that out of the many possible approach angles available to an object entering from deep space, arriving so close to the plane of the planets happens with a low probability. Estimates place the chance at about 0.02. This low probability does not prove design or intention, but it adds to the list of unusual features that need to be understood in a scientific context. The timing of the object's arrival added another detail for scientists to examine. Based on orbital models, the moment at which 3I Atlas entered the inner solar system placed it on a path that brought it within tens of millions of kilometers of Mars, Venus, and Jupiter during a single passage. These encounters were not close enough to cause major gravitational disruptions, but they were near enough for spacecraft at Mars to capture valuable data. The alignment also created a situation where, at perihelion, the object was positioned behind the Sun relative to Earth. At this point, the Sun overwhelmed all attempts to observe the visitor from our planet. Telescopes could not see through the glare, and even specialized instruments had blind zones where the Sun blocked the view. The probability of such timing, based on researchers' calculations, is around 0.00005, which means roughly 5 chances in 100,000. Because of this alignment, Earth-based observatories missed several days of activity near perihelion. This period is normally the most revealing stage in a comet-like object's journey, as heating peaks and outgassing becomes more intense. Since the Sun blocked the view, scientists could not see whether the object changed shape, released new material, or altered its trajectory. When it reappeared, some instruments detected that 3I Atlas brightened faster than expected. Its color also shifted in a way considered unusual. It appeared bluer than the Sun when measured through filters designed to track different wavelengths of light. A bluer appearance often points to strong emissions in shorter wavelengths, which can occur if certain gases or dust particles become energized. Some researchers proposed natural explanations, such as fresh, volatile materials exposed by heating. Others considered more speculative possibilities, including the idea that some internal process might have become active. These suggestions remain unproven and continue to be studied through detailed modeling. Another set of observations focused on the jets emerging from the object. Comet jets usually broaden, shift direction, and wobble as the comet rotates. They also tend to weaken or disperse as they travel through space. In contrast, the jets from 3I Atlas appeared tightly collimated. This means they extended outward in narrow, well-defined columns. These columns held their shape over distances of up to 1 million kilometers and maintained their orientation even when viewed at different angles. For a rotating object, keeping jets so steady is difficult through natural means. Each rotation changes the surface area exposed to sunlight, which typically causes natural jets to vary. In addition, the solar wind, which is a stream of charged particles moving outward from the sun, usually bends dust and gas in predictable ways. The jets of 3I Atlas did not bend or widen as expected. Scientists attempted to calculate the amount of surface area required to produce the level of gas flow observed in these jets through ordinary sublimation. Sublimation refers to the process where ice turns directly into vapor. The calculations showed that the surface area needed would have to be larger than the surface area of the whole object. This mismatch raised questions about the source of the jets. If the mass loss were distributed evenly over the surface, the object would have lost a large fraction of its mass. But preliminary images taken after perihelion showed no major fragmentation. The body appeared intact. This created a challenge. How could the object generate the observed acceleration without losing large amounts of surface material? One explanation offered was that the jets might originate from concentrated regions rather than broad surfaces. Another possibility, raised cautiously, was that the jets could resemble controlled thrust in some ways. Researchers stressed the need to explore natural explanations fully before considering alternatives. As 3I Atlas continued toward its predicted encounter with Jupiter, scientists modeled what might happen when the object reached its closest point. Based on current trajectories, this point occurs on the 16th of March in the year 2026. At that moment, the object will be moving at about 65.9 kilometers per second relative to Jupiter. This speed is much higher than the escape velocity at that distance, which is about 2.2 kilometers per second. Escape velocity is the minimum speed needed to break free from a planet's gravitational pull. Because 3I Atlas is traveling so quickly, any smaller bodies or devices that might separate from it would need to slow down significantly in order to be captured by Jupiter's gravity. Otherwise, they would simply continue past the planet. NASA's Juno spacecraft, which orbits Jupiter to study its magnetic field, atmosphere, and internal structure, has instruments capable of detecting new objects near the planet. After the close approach, Juno may search for any bodies that appear in orbits that do not match known satellites. Other missions may assist in this search. If a new object were detected that does not fit natural patterns and cannot be linked to human activity, it would raise important questions about how such an object arrived there. Scientists would need to determine whether it came from 3I Atlas or whether it had been present before but unnoticed. The discussion then turns to what such a discovery might imply. If 3i Atlas were to release something near Jupiter rather than near Earth, it would suggest that Jupiter may hold greater relevance to the object's path. Jupiter is the largest planet in the solar system. Its strong gravity, large atmosphere, and powerful magnetic field make it a dominant presence. It has been visible across interstellar distances since the early formation of the solar system. From far away, Jupiter would appear as a major gravitational and radiative source long before Earth showed signs of complex life. Researchers noted that Earth's emergence as a planet with intelligent life happened relatively recently on geological timescales. Humans have existed for only a few million years, a brief moment in the 4.5 billion year history of the solar system. If an object had been traveling for extremely long periods before reaching our system, it may have set its course during a time when Earth had no observers. In that case, the object may not recognize Earth as a significant destination. Jupiter, with its size and long-term visibility, might be the more obvious landmark from a distant point of origin. In that scenario, Earth, with its recent appearance of intelligent life, might not even register as interesting yet. The unusually low water content of the plume led researchers to examine other irregularities with greater care. As they reviewed the data collected so far, they realized that the anomalies were not isolated. Each feature seemed to connect in a broader pattern. Instead of focusing on single measurements, scientists organized every anomaly into a list and began comparing their statistical likelihoods. This allowed them to see how unusual the overall picture had become. In many fields of science, an anomaly is simply a measurement that does not fit the expected range. A single anomaly can appear for many reasons, including instrument noise or environmental factors. But when several independent anomalies appear together, and each one has a low probability on its own, researchers start testing new explanations to understand whether they are dealing with coincidence or with a deeper physical process. Once the anomalies were arranged and evaluated, it became clear that the combined picture was difficult to explain with familiar models. Each unusual feature by itself could be discussed calmly. A low water content, a retrograde orbit, or a strong dust jet might each be manageable exceptions. But when the probabilities were multiplied based on the assumption that the anomalies were independent, the numbers fell to levels that were hard to ignore. Scientists pointed out that multiplying probabilities must be done carefully, because anomalies can sometimes arise from related causes rather than from independent ones. Still, the exercise showed how far the observations had moved from the standard behavior expected of a comet-like object. One anomaly that stood out involved extreme negative polarization. Polarization refers to the direction in which light waves vibrate. When dust reflects light, the orientation of the dust grains and the way they scatter light can cause the reflected light to become polarized. Comets usually follow predictable polarization patterns. They show certain degrees of positive or negative polarization that reflect the size and arrangement of dust particles in their comae. Measurements of 2I Borisov, the prior interstellar visitor, fell within the high end of normal ranges, but the readings from 3I Atlas went far beyond these values. The negative polarization was so strong that it did not match any comet previously observed in the visible light spectrum. Researchers considered different explanations for this unusual behavior. One idea connected the polarization pattern to the strange sunward jet, or antitail, seen earlier. If dust particles were being ejected in a narrow direction and were shaped or aligned in a particular way, they might scatter sunlight differently than the dust in ordinary comets. The geometry of the antitail, combined with the possible motion of the dust through the solar wind, might produce rare optical effects. Even so, the extreme level of polarization remained one of the strongest outliers in the dataset. The measurements were repeated, checked against calibration standards, and compared across multiple instruments. The values remained consistent. Another anomaly brought researchers back to a signal detected many decades ago. In the year 1977, a powerful narrowband radio signal was recorded by the Big Ear radio telescope. It lasted about 72 seconds and came from a region in the constellation Sagittarius. The astronomer who saw the data circled it on the printout and wrote the word "wow," which later gave the signal its name. Over the years, scientists have looked for natural explanations, but none have been confirmed. The signal did not repeat, which made it difficult to study further. Although the origin remains unknown, most researchers have not taken it as evidence of artificial activity. Instead, it is classified as an unsolved observation. When scientists compared the arrival direction of 3I Atlas with the direction of the WOW signal, they found that the two were aligned within about 9 degrees. In the sky, 9 degrees is not a narrow beam. It is a broad region, but it is still specific enough that it drew attention. The estimated probability of this directional overlap is roughly 0.006, or about 6 chances in 1,000. The numbers by themselves do not suggest a direct connection, but the coincidence added another point to the growing list of unusual alignments. Scientists emphasize that coincidences do occur, especially when comparing many different features across large datasets. Still, they recorded the alignment as an item worth further study. As each anomaly was placed on the list, researchers looked for the key observation that might distinguish between natural and non-natural explanations. Many of them pointed to the need for detailed spectroscopic measurements of the jets. Spectroscopy is a technique that separates light into its component wavelengths. Each chemical element and molecule produces characteristic patterns when it emits or absorbs light. These patterns act like signatures. If the jets of 3I Atlas come from natural sublimation, the spectra should show familiar lines associated with water vapor, carbon monoxide, carbon dioxide, methane, hydrogen cyanide, or other common cometary gases. Their relative strengths would tell scientists whether the jets match known activity patterns. But if the jets come from some form of powered exhaust, the spectra would look very different. They might show temperatures too high for ordinary sublimation, unusual molecular fragments, or emission lines inconsistent with known comet chemistry. Velocity profiles, meaning the speed distribution of particles within the jets, could also help distinguish between natural and non-natural processes. A natural jet produced by sunlight heating a surface tends to have a spread of speeds and directions. An engineered exhaust would likely produce a more controlled and uniform flow. Researchers therefore identified spectroscopy as one of the most important next steps for understanding the nature of 3I Atlas. Since emerging from behind the sun, the object began showing new patterns of brightness, Observations indicated that it had become noticeably brighter than before perihelion, and changes appeared in the ultraviolet and X-ray wavelengths. Comets are sometimes known to emit X-rays when solar wind particles interact with their comae. However, the strength and timing of the activity observed here raised questions about what triggered the increase. The color contrast of the object also became more pronounced, with a stronger shift toward shorter wavelengths. Scientists asked whether this change came from new material being exposed, from a shift in the balance of gases, or from interactions between the jets and the solar wind. Images from NASA's Mars missions provided more insight into the object's structure. The high-rise camera on the Mars Reconnaissance Orbiter had previously captured a coma roughly 1,500 kilometers wide. Further analysis of those images, combined with new data, may allow scientists to estimate the size of the nucleus more accurately. The nucleus is the solid central body, buried beneath the surrounding cloud of gas and dust. Determining its size helps to place limits on the mass, density, and surface properties of the object. The color of the dust particles in the coma also offers clues about the object's age. Dust that has spent long periods exposed to cosmic radiation tends to darken over time and may develop specific spectral signatures. MAVEN's ultraviolet observations set upper limits on the ratio of hydrogen to deuterium in the gases surrounding the object. Deuterium is a heavier isotope of hydrogen that contains a neutron in its nucleus. The ratio of hydrogen to deuterium varies across different regions of space. For example, comets formed in the outer solar system tend to have higher deuterium levels compared with water on Earth. By measuring this ratio, scientists can infer the environment in which an object formed. In some cases, the ratio serves as a kind of isotopic fingerprint, offering clues about stellar nurseries or interstellar clouds. The measurements from MAVEN were not precise enough to determine the exact birthplace of 3I Atlas, but they helped set boundaries that may be refined with additional observations. Even the Perseverance rover on Mars contributed meaningful data. Observing a faint object from the Martian surface is not simple. Although Mars has a thinner atmosphere than Earth, dust in the air can scatter light and obscure faint sources. The rover had to use long exposure times to capture even a dim trace of the object. During these long exposures, background stars appear as streaks because the rover and the planet are both rotating. Against that background, 3I Atlas appeared as a faint point that did not smear across the frame. The fact that the rover could detect it at all shows how bright the object had become after perihelion. As scientists reviewed the anomalies, they also paid attention to how NASA presented the information during a press conference held on the 19th of November. The agency described 3I Atlas as a comet and emphasized natural explanations. This approach reflects the scientific method. Researchers generally prefer to start with the simplest models that fit the data and only expand to more complex hypotheses when the evidence requires it. Extraordinary claims demand extraordinary evidence, and so far, the anomalies, while striking, had not yet pointed conclusively to a non-natural source. At the same time, scientists acknowledged that the combined list of unusual features represented a challenge for existing models. The probability values discussed across different reports varied depending on the assumptions used for the calculations. Some anomalies, such as the alignment with Jupiter's Hill radius or the retrograde but ecliptic level trajectory, had estimated probabilities of only a few chances in many tens of thousands. Others, such as the directional match with the wow signal, had probabilities on the order of 6 chances in 1,000. Each anomaly might still be explainable within the broad range of natural behavior. However, the approach of multiplying their probabilities highlighted the tension between randomness and pattern. In theory, if several independent low probability events occur together, the combined likelihood becomes extremely small. Scientists emphasized that probability multiplication requires caution. Anomalies can appear independent on the surface yet stem from shared factors. For example, the shape of the jets, the polarization of scattered light, and the measured brightness might all be influenced by the same internal structure. In that case, they should not be multiplied as separate probabilities. Even so, the exercise illustrated how far the object diverged from typical comet behavior. As the numbers were combined, the results entered ranges so small that they prompted researchers to examine the underlying physical assumptions once more. While the data did not justify definitive conclusions, the combined probability pushed the discussion toward questions about the basic assumptions used to interpret the data. Because the earlier findings raised questions about basic assumptions, researchers continued to examine the growing list of observations with these concerns in mind. They understood that caution was essential. In science, unusual claims must be supported by strong evidence, and this principle guides how astronomers respond to unexpected data. Even so, the evidence around 3I Atlas continued to expand. Each new measurement added another detail that did not easily fit into familiar categories. The goal was not to draw fast conclusions, but to understand how all the pieces could be explained with processes known to occur in nature. As the list became longer, researchers recognized that they were dealing with a case that required patient, methodical study. If one begins with the simplest assumption that 3I Atlas is an ordinary comet that happened to enter our solar system, there is still a significant amount to consider. The first observation to confront is the object's mass. It is estimated to be roughly 1 million times more massive than the first interstellar visitor detected, which was Oumuamua, pronounced O-U-Mu-A-Mu-A. It is also estimated to be around 1,000 times more massive than the second interstellar visitor, 2I Borisov. In the context of interstellar objects, such mass stands out. Large bodies can exist between stars, but current models suggest that very massive objects should be rare. Observing one on a trajectory that brings it into the inner solar system, where it can be studied at close range, is unusual by itself. The second observation concerns the path of the object. 3I Atlas moves in a retrograde direction, meaning it travels opposite the direction of the planets around the Sunday. Retrograde motion is not extremely rare, but it is not common either. What makes the trajectory more striking is its alignment with the ecliptic plane. The ecliptic plane is the broad, flat layer where most planets orbit. Objects entering the solar system from interstellar space usually approach at many different angles, often quite steep compared with the ecliptic. Yet 3I Atlas approached within a few degrees of this plane. When combined with the fact that it came from an unusual direction, the alignment made researchers take note. The estimated probability for such a match is low, though probability alone is not enough to determine cause. A third observation involves the timing of its arrival. Based on orbital models, the object entered the inner solar system at a moment that placed it near Mars, Venus, and Jupiter at different stages of its journey. Its perihelion, which is its closest point to the Sun, occurred when it was positioned behind the Sun from Earth's point of view. This configuration blocked Earth-based telescopes from observing the object during one of the most informative stages of its orbit. The chance of this exact alignment is also small. Scientists do not assume intention from these coincidences, but they record them because they influence what data can be collected. The fourth observation involves non-gravitational acceleration. At a critical point in its approach, 3I Atlas changed its motion in a way that cannot be attributed to gravity alone. Many comets experience non-gravitational acceleration due to gas escaping from their surfaces. However, the direction and magnitude of the acceleration observed here matched the amount needed to guide the object toward Jupiter's Hill radius. The Hill radius marks the area where Jupiter's gravity becomes stronger than the Sun's gravity. Reaching this boundary with such precision is unusual, and researchers therefore examined the data carefully to ensure that common physical processes could produce the observed shift. A fifth observation concerns the jets released by the object. Jets on natural comets typically change direction as the comet rotates. They also widen as they move through space. The jets on 3I Atlas, however, remained narrow and held their orientation over very long distances. These jets extended across many hundreds of thousands of kilometers while maintaining their shape. The consistency of the jets suggested some kind of stable process. Researchers considered whether the jets might come from specific areas on the surface, or whether internal heat patterns could channel them in a stable direction. The calculations showed that the surface area needed for such strong jets exceeded the estimated surface area of the entire object. That meant something did not align with standard sublimation models. Another unusual observation involved the object's composition. The plume contained high levels of nickel relative to iron, with ratios that resembled certain nickel-rich mixtures rather than typical cometary materials. This difference did not prove anything by itself, but it added to the list of features that did not match what researchers expect from a natural comet. The water content measured only about 4% by mass, while most comets in the solar system are dominated by water ice. Other measurements showed that 3I Atlas brightened rapidly and changed color in ways that depart from familiar activity patterns. These changes were documented before and after perihelion, raising questions about what processes were taking place while the object moved behind the Sun, out of sight from Earth. Finally, scientists observed that the direction of approach aligned with the region associated with the narrowband radio signal known as the WOW signal, detected in the year 1977. The WOW signal lasted about 72 seconds and has never been explained with certainty. Most researchers do not consider it evidence of artificial activity, but because 3I Atlas arrived from a direction within roughly 9 degrees of that signal, the coincidence was noted. The probability of such a match is estimated at about 6 chances in 1,000. While not overwhelming by itself, it contributed to the broader discussion. These observations, when listed separately, represent a series of unusual but not impossible events. Any one of them could be a result of rare but natural conditions. Together, they create a pattern that scientists cannot dismiss without careful evaluation. This is where the scientific method becomes essential. All possible explanations must be explored, including those that challenge existing assumptions about what interstellar objects are like and how they behave. Researchers do not begin with conclusions, they begin with questions, and in this case, the questions have multiplied as the dataset has grown. The months ahead will be important for clarifying these uncertainties. As 3I Atlas continues its journey, telescopes across the world will monitor its movement, brightness, and color. More instruments will measure its chemical signature. Spectroscopic analysis of the jets is one of the most promising pathways for understanding their origin. Spectroscopy separates light into its component wavelengths, allowing scientists to identify molecules based on their distinct patterns. A natural jet formed by sublimation would contain familiar signatures such as water vapor, carbon monoxide, carbon dioxide, methane, or hydrogen cyanide. If those signatures appear in expected proportions, the jet mechanism may resemble that of a natural comet. If the jets come from a different kind of process, the spectra would reveal that as well. High temperatures, unusual chemical fragments, or sharply defined emission lines could indicate mechanisms that do not match normal comet activity. Researchers plan to analyze velocity distributions within the jets, studying how fast particles move and how evenly their speeds are distributed. Such measurements can help distinguish between natural and controlled flows of gas. The more complete the dataset becomes, the easier it will be to test competing hypotheses. Observatories will also track changes in brightness and color. 3I Atlas grew brighter after emerging from behind the sun, and it displayed activity in the ultraviolet and X-ray wavelengths. Observing how these features evolve as the object travels farther from the sun may reveal whether the changes result from the heating cycle, from interactions with the solar wind, or from processes inside the object. Similar analysis will focus on how the coma expands or contracts, and whether new jets appear or existing jets weaken. The approach to Jupiter in the year 2026 will be another major moment. Jupiter's massive gravity affects the paths of many bodies. If 3I Atlas releases smaller objects or fragments near the Hill radius, those bodies could slow enough to remain in orbit around the planet. If any new satellites appear that cannot be traced to known missions or natural sources, they will be examined closely. NASA's Juno spacecraft, already orbiting Jupiter, will be in a position to detect unusual activity. Ground-based telescopes and other orbiters will also watch carefully. The observations collected during this time will form an important part of the scientific record. Regardless of the outcome, even if nothing is released near Jupiter, the scientific questions will remain. Researchers will still need to explain why so many independent measurements appear to fall outside expected ranges. They will have to address the statistical challenges posed by the combined anomalies. They will have to decide whether current models of interstellar bodies can be adjusted to include objects like 3I Atlas, or whether deeper revisions are required. The object's mass, trajectory, composition, and jet behavior each raise questions that can be studied independently and together. 3I Atlas will make its closest approach to Earth on the 19th of December in the year 2025. At that moment, it will be about 2 astronomical units away, or roughly twice the average distance between Earth and the Sunday. This distance poses no threat to Earth, but it is close enough for detailed observations. Amateur astronomers with suitable equipment may attempt to capture images, while professional observatories will monitor the object in multiple wavelengths. As it moves away from the Sun, scientists hope to track changes in its jets, composition, and brightness. They will watch for signs of fragmentation or fading, and they will measure how the object responds to the decreasing solar radiation. The uncertainties remain broad. The object may continue to brighten, or it may dim as its outer layers cool. New jets may appear, or the existing jets may weaken. Its chemical composition may shift as different ices sublimate or freeze. Alternatively, it may behave in ways that have not been documented for comets before. Any of these outcomes would provide valuable information for refining models of interstellar bodies. The larger questions involve how this object fits into the small but growing set of interstellar visitors observed so far. Oumuamua exhibited unusual acceleration and an irregular tumbling motion that scientists could not fully explain with common comet models. 2I Borisov appeared more typical, showing behavior consistent with known comets, which helped confirm expectations about what interstellar comets might look like. 3I Atlas, however, has displayed an array of features that extend beyond both of those earlier cases. Each new observation seems to move the object farther from familiar categories, pushing researchers to consider explanations outside the range they had expected. In this sense, the series of interstellar visitors has gradually moved from the understandable toward the unfamiliar, pushing us further from comfortable explanations. As researchers continued sorting through the anomalies already documented, they also began preparing for the observation window ahead. The period leading up to the 19th of December, in the year 2025, would offer a final chance to gather data before 3I Atlas moved farther from Earth on its way toward Jupiter. In astronomy, there are moments when an object's position and lighting conditions create a brief but valuable opportunity. This was one of those moments. With each passing week, observatories refined their plans, adjusted schedules, and coordinated time across multiple instruments to ensure the best possible coverage. The aim was simple: capture as much information as possible while the object remained within reach of high-resolution measurements. Across the world, teams prepared spectroscopic observations designed to study the jets in detail. Spectroscopy works by separating light into different wavelengths. Much like a prism creating a spectrum, every element and molecule produces distinct patterns within that spectrum. Those patterns allow scientists to identify chemical compositions, estimate temperatures, and measure particle velocities. If the jets come from natural sublimation where ice transforms directly into gas, then the spectrum should reveal well-known signatures: water vapor, carbon monoxide, carbon dioxide, methane, hydrogen cyanide, and other familiar molecules would produce recognizable patterns. Their relative strength would also show how much each contributes to the plume. If the jets arise from a process not driven by natural sublimation, the spectroscopic signals would likely differ. Gas temperatures might exceed what is expected from sunlight alone. The velocity distribution might be narrower or more structured. Emission lines might appear in unusual ratios. Any of these outcomes would guide researchers toward new models that could explain what they were seeing. Because spectroscopy records light rather than physical samples, It provides one of the most direct methods available for assessing the jet mechanism at a distance. Scientists therefore placed considerable emphasis on this upcoming set of measurements. Chemical analysis would also continue beyond spectroscopy. Ground-based telescopes, equipped with modern sensors, can measure subtle changes in color, brightness, and reflectivity. These measurements, collected over time, create what researchers call a light curve that reveals whether an object's activity is increasing, decreasing, or shifting from one dominant material to another. New detectors allow observers to see faint details that previous generations of astronomers would not have been able to detect. Changes that once required large observatories can now be documented by a global network of instruments working together. As 3I Atlas begins its departure from Earth after the 19th of December, it will continue toward its predicted encounter with Jupiter on the 16th of March in the year 2026. Those months of travel represent an important stage in the object's evolution. When a body leaves the region near the Sun, the solar energy striking its surface decreases. For natural comets, this usually means declining activity. Jets weaken, brightness fades, and color shifts as outer layers cool and volatile material becomes more stable. If 3I Atlas behaves like a natural comet, researchers expect to see a gradual settling into patterns that match familiar models. But if the earlier anomalies reflect something not driven entirely by standard cometary processes, the object may continue to show unexpected behavior. New jets may appear as different regions of the surface, warm or cool. Brightness may fluctuate in ways that do not align with solar heating alone. Color may shift again if new materials are exposed, or if the surrounding dust cloud changes in density or composition. All of these possibilities remain open questions, and many observatories will monitor the object closely during this interval. As the encounter with Jupiter approaches, researchers will also consider what might happen if objects separate from 3I Atlas near the Hill radius. Jupiter's immense gravity dominates a large volume of space. For any fragment or device to remain orbiting Jupiter, it would need to slow significantly relative to the visitor's high speed. Natural fragmentation is possible, especially if internal stresses become too strong, but such fragments rarely enter stable orbits without specific conditions. If new objects were detected around Jupiter that cannot be traced to known missions or natural moons, they would undergo careful scientific analysis. Jupiter already hosts dozens of small, irregular moons, so any new discovery would need to be distinguished from background objects. This task requires detailed tracking and comparison with existing catalogs. Speculation about non-natural origins occasionally appears when objects behave in unfamiliar ways, and 3I Atlas has prompted some discussions along these lines. One common question raised is why, if the object were artificial, there has been no clear attempt to communicate. From a scientific perspective, communication assumes a shared set of priorities or intentions. An intelligence capable of traveling between stars could operate on timescales vastly different from those familiar to humans. Processes that take minutes or hours to us may hold no significance in a broader cosmic context. It is also possible that an object entering the solar system is not an active vessel, but an automated probe sent long ago by an origin point that has since changed or no longer exists. These possibilities remain speculative. What matters for researchers is not the assumptions but the evidence. Each hypothesis must be tested against the data. If natural models fail to explain the observations, then new frameworks must be developed. If natural mechanisms can explain the findings, they should be favored until proven otherwise. This approach is central to the scientific method. It allows theories to evolve while ensuring that conclusions remain grounded in measurable facts. The presence of open questions is not a weakness, but a signal that additional study is needed. Meanwhile, astronomers are tracking 3I Atlas with an intensity rarely seen for an interstellar visitor. Telescope time is being scheduled across multiple facilities. Requests for observation slots have increased as teams compete to gather information before the object moves too far to study in detail. Research groups are publishing new analyses at a rapid pace. Some focus on the jet structure, others on the composition of the dust, and others on orbital models attempting to explain why the trajectory aligns so precisely with Jupiter's region of gravitational influence. The scientific conversation is active, and the exchange of ideas is brisk, reflecting the high level of interest generated by each new observation. When unusual objects appear, scientific understanding often grows through comparison. In earlier studies, researchers believed that interstellar bodies would resemble the icy remnants familiar within the solar system. The arrival of Oumuamua challenged this expectation by exhibiting a shape, rotation pattern, and acceleration that did not fit neatly into comet or asteroid categories. 2I Borisov offered more conventional behavior, reinforcing the idea that many interstellar objects might resemble ordinary comets. Then came 3I Atlas, showing a combination of mass, color changes, jet patterns, composition, and orbital details that have pushed existing models beyond their comfortable limits. Each case expands the range of what scientists must consider when studying objects originating outside the sun's influence. The rapid pace of scientific papers, conference discussions, and observation proposals reflects how strongly this object is reshaping expectations. In some ways, the last few months resemble earlier periods when a surprising discovery reshaped an entire field. When gravitational waves were first detected, the volume of related papers surged as researchers explored new applications for the data. When the Higgs boson was confirmed, particle physics experienced a similar period of concentrated activity. Now, with 3I Atlas, the astronomy community is experiencing a comparable wave of analysis as they work to reconcile data that does not neatly align with familiar categories. What stands out in this situation is how the object highlights the current limits of our knowledge. Humanity has explored its own solar system with increasing sophistication. Spacecraft have landed on comets, sampled their dust, and studied their internal structures. Models have been built from decades of observations and direct measurements. Yet, all of this experience comes from a single star system. Beyond it lies a galaxy filled with environments we have never studied directly. Interstellar space may produce types of bodies that differ in key ways from those we encounter at home. 3I Atlas may be an example of such diversity, or it may indicate something else entirely. Either possibility offers valuable insight. As the 19th of December approaches, researchers continue refining their observation strategies. They expect to gather measurements across visible light, infrared, ultraviolet, and radio wavelengths. each wavelength reveals different information about temperature, composition, and particle size. Instruments will record how the coma evolves and whether new jets appear. Astronomers will also analyze how the object responds to decreasing solar radiation as it moves outward. These data will help determine whether its behavior follows known patterns or deviates again in ways that require new theoretical explanations. After that date, attention will begin shifting toward the encounter with Jupiter. The weeks leading into the year 2026 will likely bring new measurements that show whether the object continues to behave unusually or settles into expected comet-like activity. Some researchers anticipate that the jets will weaken as the object cools. Others expect that deeper layers could release new materials as earlier layers are removed. Still others focus on the potential appearance of small fragments or dust features that could offer clues about internal structure. Each possibility represents an opportunity to learn something new. No matter what is discovered, the effort to understand 3I Atlas will continue. As with any scientific investigation, the most reliable answers will come from consistent measurement, careful comparison with theoretical models, and cautious interpretation. The goal is not to confirm pre-existing ideas, but to build explanations that match the full set of available data. The case of 3I Atlas demonstrates how scientific understanding grows when unexpected observations force the re-examination of earlier assumptions. In the months ahead, continued monitoring and analysis will shape the developing picture. The behavior of the jets, the shifts in brightness, the changes in color, the evolving path toward Jupiter, and the chemical signatures detected across different wavelengths will all contribute to a clearer understanding of the object. As scientists work through this information, they will refine their interpretations and adjust their models accordingly. And as these refinements accumulate, the nature of 3I Atlas will gradually become more defined. However the observations develop, they will expand our understanding of interstellar visitors and the processes that shape them. Even if future measurements reveal that the object belongs to a natural class not yet documented, that would deepen our picture of how materials form and evolve beyond the solar system. If the measurements suggest something different, then new scientific frameworks will emerge to account for the data. In either case, the object represents a meaningful opportunity to learn, and as the observations continue, the scientific discussion is likely to evolve in step with each new piece of measurable evidence, fading into a period of patient study as researchers follow the data to whatever understanding it supports.